This is Mr. Hausman. Good morning. We're going to be working on electricity today. You've already previewed the Professor Dave video on potential difference and current and resistance, but I thought I'd give you a little more perspective that lines up a little bit with our skeleton notes that I've already uploaded to Canvas. So this video is kind of specific to Connect 2.0, and let's get started. So you should be able to see me and kind of a blank page. I'm using Explain Everything, but what would be ideal would be for you to download the most recent Canvas posting, that is to say the packet on electricity. This is the first page of it. Hopefully you can see that. You do not need to print every page, but I'm going to be doing notes that would essentially be on the front cover, kind of giving us some background information, as well as then you'll notice on a couple of slides later, I'll be right on page 2 and even page 3 of our packet. So your first assignment is to kind of an introduction to electricity, electrical potential, and current today. So let's begin. So electricity is nothing more than the movement of charge, in a conductor. The two most common conductors are things like solid metals or solutions. Some of you know well the chemistry of solutions, and one of their properties is if you have dissolved ions that you can conduct electricity through them. We'll be primarily focusing on solid metal conductors and save electrochemistry for kind of a chemistry course or more advanced physics course. And while they do so, they carry electrical potential energy. So we've all mastered electricity. We turn on switches, we turn on lights, we charge up our phones. All you're doing is learning how to use mechanical systems to move charges. Most of the time, I bet some of you have the idea that electricity is about electrons, but as it turns out, electricity can be thought of as either moving positives, protons, or moving electrons, negative. And we'll be talking about both. In reality, electricity is moving electrons, but having to do with some historical information. Sometimes you can think of it both ways. So next up, let's talk about electrical potential energy. We definitely did not quite finish our unit on everything we were going to cover on electric fields. But you should hopefully recall that an electric field is created from a single point charge or from parallel plates. And electric fields always go or point from the positive and go toward the negative. So this would be called a uniform electric field because parallel plates would have an E field that would be the same no matter where you were anywhere between the plates. And that's drawn by 3 parallel lines that are evenly spaced out. So that's an E field, and the abbreviation for an E field is, of course, capital E. So E fields by themselves don't make electricity. What they can do, though, is they can do work on charges. So if we were to drop a positive charge into that E field, and we were to position it near the positive, well, you know right off the bat that that positive would be repelled. Well, what does repel mean? Repel means it gets pushed. There would be a force on this, and the name of that force would be, right, Fe. And it would get pushed farther and farther away from the positive, and it would also be attracted to the negative. So it's actually being pushed and pulled at the same time. So what we talk about here is that this is kind of like putting a positive where it doesn't want to be. It's being repelled. It's in a distressed state. It will want to move away from there. Think of that like pulling back a rubber band on a slingshot or just a regular office rubber band. When it's pulled back, when the positive charge is near the positive plate, that's a high amount of potential energy. So the potential energy it has here is increased. It's much higher. But what kind of what kind of potential energy is this? It's electrical. So this would be high potential energy. Well, by the time the positive has moved down here, it has low potential energy. And think about that. You actually know a perfect metaphor for this in gravity. The way gravity works is there has to be a large mass, or some kind of mass, it creates a gravity field, little g. And for humor, we're going to say that let's pretend G is uniform and it's always parallel. We know that it actually points toward the center. But for two people who are close together, those two lines would be about parallel. So we have a G field here. Well, again, gravity by itself doesn't do anything to you until you, right, your mass basically is no longer supported by another force. You let gravity take over. And this field, called a G field, causes this mass to experience, right, the force of gravity. So while doing so, you know that you have potential energy at the top, and that's going to be high amounts of potential energy and low amounts of potential energy at the bottom. So see, this perfect metaphor exists for something that you kind of know well, how masses get affected by gravity. They feel forces and they would, of course, accelerate. They have high amounts of potential energy at the top and low amounts at the bottom. Uh, and going back over to the electrical side, right? High potential energy when the charge is near where it quote unquote doesn't want to be, which is basically near its similar charge. So there's a formula that we can derive for how to figure out the amount of energy you have. And we won't be using this quantitatively, but we're going to introduce it. It's equal to negative Q E D. Q stands for the charge. That should be something we remember. E stands for the how big the E field is. And D is the displacement. How far is the charge away from its starting point or from its reference point? And so when you get that, you get how many joules of energy. Coulombs times newtons per coulomb times meters, and you're going to come up with potential energy. But the unit, of course, or the type is going to be, of course, electrical. So let's kind of box that formula. Want to see a coincidence? Let's look at the formula for potential energy due to gravity. M times G times H. Well, here's the ironic part. M is like Q. It's the quantity you have to have, the object has to have, either the tiny little charge right here, or the mass, the parachuter that I have falling in this picture, right? This object has to have a charge to feel any force. This object just has to have mass. So basically it's a property of the object that's in the field. G over here is the is the gravitational field. E is the electric field. And D is basically your position, your height. How far away are you from the negative terminal? So I see kind of a weird coincidence that essentially these two formulas, although very different, have the same three variables. They have a quantity that describes the material, a field, and a distance. So electrical potential energy is based on where a charge is in a field. Okay, so where are these fields found? Well, guess what? They're in batteries. They're in the wires of your house. An electric wire has an E field that goes from one end to the other. Okay, now modern electricity is a little more complicated. For those of you who are going to become electrical engineers or do large systems like power grid engineering, you're going to find out about there's a difference between direct current and alternating current. Not the topic for today, but essentially you can think of a wire carrying electricity as having a positive end and a negative end, and that creates an electric field the entire length of the wire. Let's go to the next slide. So if electrical potential energy is a property you have in an electric field, then what actually drives the electricity in a wire, right? We're studying electricity. Well, potential difference is when you have a wire that has maybe a positive end and a negative end that are hooked up to a battery, and the battery drives the electricity. But essentially what you have is you have charges that have high potential energy here on one end. They have low potential energy on this end. And the difference between those, or the difference between the two sides of the two different positions, is called the potential difference. Professor Dave doesn't tell you that there's a nickname for that, and that's called the voltage difference, or just the voltage. So batteries always have positive and negative terminals. And here they are. 9-volt has the positive is the circle, and the post is the negative. The positive is the nub on a AA or a AAA battery, and the flat part is the negative. And then in a car battery, right, they're clearly labeled positive and negative. So a battery, we sometimes call it a 9-volt battery, but in reality, what this is a change in voltage of 9 volts from the positive to the negative end. There's a 1.5 volt difference for a AA battery or a AAA battery. And you might say, wait a minute, why would they make two batteries that have the same voltage? Well, it has to do with how long they will last. A AAA battery is used for when you don't need much energy at all. It can only store a certain amount. AA's are bigger. C batteries, D batteries, they're all 1.5 volts. So it's the difference in energy the charges get from one end to the other. So car batteries are a little different. When you hook up a car's circuit and all the electronics in there, and you check the wire, you're going to find out that your battery is giving you 12 volts. Now, sometimes it's more, sometimes it's less, but the what's called the nominal, the regular value. So there's a new formula we can do for potential difference. So the formula for potential difference is delta V. Remember, that is the potential difference, is nothing more than the change in potential energy divided by charge. Now, what that really does by dividing by charge is you know that in this wire, this is a wire made of metal, that there's probably some electrons moving around in there. And we're going to talk about that on the next slide. So it's kind of like a ratio of how much energy is each coulomb of charge carrying. Now, carrying is a human property. You can't really carry charge, but you can think of it as electrons in wires. That's what electricity is. They can have different amounts of energy. There can be high voltage wires, and they carry a lot of energy in the electrons, or you can have a low voltage wire, and that carries not much energy or less energy. So let's talk about kind of some of the units. What's the unit for voltage or potential difference? Well, the unit, confusingly or really simply, if you think about it, is the unit is the volt. It's named for Alexander Volta, but that's the unit, right, for voltage. So what is 1 volt? It's when 1 joule of energy is shared by 1 coulomb of charge. When I say shared, remember a coulomb of charge is a lot of electrons. Again, an older skill, and we could review that if we need to. So there's electrical potential or electrical potential energy. Now there's potential difference. If you have a potential difference between the positive and negative terminals that's 0, if they have the same energy, electricity will not flow. That was what we would call a dead battery or basically a circuit that will not flow. So finally, we get to a page that looks like something you have. And we're going to introduce current, and then we're going to have you practice current. And that's going to be the first lesson. So current, like the word you already know from maybe a river or thinking about a stream, is now we're talking about something very specific. We're talking about the movement of charges and how we measure those. Well, let's talk about first what current is. Voltage is the first concept. Current is kind of the second fundamental concept. A conducting wire is filled with loose electrons. They are valence electrons that are not tightly held by their nucleus. They are almost shared between different atoms. And what they do is they bounce around like crazy all the time, depending on the temperature of the metal, right? But they have something called a thermal velocity. At different temperatures, those electrons, but the motion is totally random. There is no direction to the movement. You can see in that picture. They're going every which way. They're kind of interchanging, but they're like a game of elbow tag. Can you relate to that? But they never stick around one place for long. So what if there's no E field? Let's take this piece of metal, and let's start with no E field. That is to say, the wire either has the same energy on both ends, or it's not even hooked up, right? So if there's no electric field along the wire, there is no electric force to push the charges along, right? To force them along. Forces cause pushes. So if you stood at a single spot along the wire, you wouldn't notice that the electrons aren't moving at all. But what they aren't doing is they're not moving in one general direction. The motion is random. So what we would say is that the current here, right, there is no net movement. So the current is the number of charges flowing per second, and there would be no overall or net movement. Sure, there'd be random movement, but it wouldn't be in one direction. Okay, the moment you have an E field, something happens. The moment you have hooked up your wire to a battery, now the E field, and notice there is a direction to it, the E field is going this way. So that means the positive terminal of the battery must be over here, the negative terminal is here. And these electrons are wandering in a general direction. They're not going in a straight line. It's kind of like water flowing through rapids. The water doesn't just go straight down. It hits a rock, it hits a rock, it hits a branch, but it's bouncing off things. But its overall motion, right, of the electrons, right? Electrons are moving to the right. And now we have a measurable current. Here, the I would be 0. Here, the I would be something other than 0. That's a not equals to. Okay. So what is current? How do we measure it? I've kind of already alluded to it. It's the amount of charge or coulombs of charge that pass a point in a second per unit of time. And the formula is I equals Q over T, where I is the current in amperes, Q is the charge in coulombs, and T is the time in seconds. Let's practice that. Kind of the first and going to be the easiest level of electricity problems. So the formula is at the top, I equals Q over T. That can, of course, be rearranged to solve for Q or T. But I'm going to do one together and see if it makes sense. So I equals Q over T. And why do I know to use that? Well, it's a practice page, but I have 6 coulombs of charge. So my Q is 6 coulombs. I have a time of 5 seconds. So what is my current? So there's my formula. Then I plug in 6 coulombs over 5 seconds. And that's going to be 1 1/5 or 1.2 A's. So we haven't really mentioned that, or I glanced over it. An A stands for an ampere. That's the unit of current you get. When you have 1 coulomb flowing per 1 second, it's referred to as 1 ampere. So that's the unit we use for all current calculations. Your assignment today is to do a few more of these current problems, and definitely a great start on electricity for today. Let me know if you have any questions.